Let's continue the discussion on the flux through any closed surface. Consider a positive point charge Q in space. Now we have a sphere with a radius r concentric with the charge Q as shown in this figure. The magnitude of the electric field everywhere on the surface of the sphere is expressed by this equation. The field lines are directed radially outward and hence are perpendicular to the surface at every point. Therefore, the electric field at each point on the surface is parallel to the vector dA. Let's find the net flux through this spherical surface by the integral of E over the surface, where we have moved E from the integral side because E is constant over the surface. And the area of the surface of the sphere is 4 pi r squared. Substitute E and A and then solve for the net flux through the surface. This equation shows that the net flux going through the spherical surface is proportional to the charge inside the surface. We found that the flux is independent on the radius r because the area of the spherical surface is proportional to r squared, whereas the electric field is inversely proportional to r squared. Therefore, in the product of EA, the dependence on r cancels. Now consider several closed surfaces surrounding a charge Q. Please look at this figure. The S1 is spherical, but the S2 and the S3 are not. According to the formula we obtained for the spherical surface, we know that the flux over S1 equals Q over epsilon 0, which is proportional to the number of electric field lines penetrating a surface. From this figure, we can find obviously that the number of lines through the S1 is identical to the number of lines through the non-spherical surfaces S2 and S3. Therefore, the flux over these three surfaces is the same and independent on the shape of the closed surface. Let's consider another case. A point charge is located outside a closed surface. From this figure, we can find that any electric field line entering the surface must leave the surface at another point. In other words, the number of electric field lines entering the surface equals the number of lines leaving the surface. Therefore, the net electric flux through a closed surface that surrounds no charge is 0. Hence, the flux through a closed surface does not depend on the charges outside the closed surface. Based on the discussion above, we could have the following conclusion. The net flux through any closed surface equals the net charge enclosed by the surface divided by epsilon 0, which is expressed by this equation, where E represents the electric field at any point on the surface and Q in represents the net charge inside the surface. When we employ this equation, please note that the charge Q in is the net charge inside the surface, but E represents the total electric field, which includes the contributions from all charges both inside and outside the surface. This is Gauss's law. Gauss's law is one of the most important laws in the study of electric fields. Gauss's law describes a general relationship between the net electric flux through a closed surface and the charge enclosed by this surface. This closed surface is called Gaussian surface. Gauss's law gives us the property of the electric field, which can be used to determine the electric field in principle. But in practice, it's applicable only in a limited number of highly symmetric situations. To determine the electric field due to the symmetric charge distributions, the key is to choose a suitable Gaussian surface. Next, we'll discuss how to employ Gauss's law to determine the electric field for charge distributions that have spherical, cylindrical, and planar symmetry.